So today we're going to be looking at quality of tests. And through this chapter we're going to be analysing hypothesis tests. Not only are we getting the conclusion of whether we reject H0 or not, but we're also then going to check whether that was the right decision to make. So we're going to start off by looking at type 1 and type 2 errors. So here we have a familiar situation. Josh is playing a game. He has a three-sided fair spinner, and he'll get 1 point if it lands on win. One of the sides of the spinner allow him to win, and for two of them, he's going to lose. He spins the spinner 10 times, and he gets 7 points. He won 7 times. His friends are looking at him and thinking that he must have cheated. He did something to make the spinner land in his favour. He's manipulated or he's hacked the spinner. We could do a hypothesis test to make a conclusion on whether or not we think that Josh is cheating or Josh is actually playing fair. The null hypothesis, P equals 1/3. Josh was not cheating, he was playing fair. The alternate hypothesis, P is greater than 1/3. This is the case that Josh cheated. He's done something to make the probability of him landing on win greater than 1/3. Okay, so in a hypothesis test, as usual, we can calculate the critical region. Critical region has been calculated with a 10% significance level, and the critical region is x is greater than or equal to 6. So we will be suspicious if there are 6 or more wins for Josh. He won 7 times. 7 is in the critical region. We're suspicious that he's cheated, and we conclude our hypothesis test by saying there's enough evidence that P is greater than 1/3, which in turn means we think Josh has cheated. Although this is the conclusion to our hypothesis test, there's a chance, and there's always a chance, that we're actually wrong. And Josh just got lucky, and he got 7 wins out of the 10 attempts. There's a probability that that happens. There's a small probability, but it's there nonetheless. In reality, there's an actual probability that he gets 10 wins in a row. Very small probability, but it exists. When we reject H0 when we shouldn't have, this is known as a type 1 error. When we pull up Josh and tell him that we know he was cheating when actually he innocently got those 7 wins, this is called a type 1 error. Now this relates directly to the significance level. We aimed for a 10% significance level. We wanted there to be no more than a 10% chance that we came to the wrong conclusion. Because of the way discrete distributions work, we actually had a significance level of 7.66%. But that 7.66% is where we assume that there's something wrong with H0. We assume that Josh was cheating, and that may not have been the case. What about the other way around? What if Josh had only got 5 points, but he was desperately trying to cheat, just wasn't good at it? Well, that would not be in the critical region, and our hypothesis test would not have indicated or led to us thinking he was cheating, and he would have got away with it. A poor attempt at cheating, he only got 5 successes, but he would have got away with it. Once again, our hypothesis test led to the wrong conclusion. This time round, we've incorrectly accepted H0. This is known as a type 2 error. So, let's just summarize the 4 potential outcomes to a hypothesis test. In the columns, I have the actual truth of the hypothesis, whether H0 was actually correct or H1 was actually correct. And in the rows, I have the conclusion that we got from the hypothesis test. So there are 2 regions where our hypothesis test served its purpose perfectly. Where we accept H0, and it should have been accepted. And when we reject H0, and we should have rejected it. Where we accept H0, and it was actually correct, so that's top left. And when we reject H0, and H0 was wrong. Bottom right. Top left, that would be a doctor concluding that someone doesn't have a disease and that person doesn't have the disease. Bottom right, that would be the doctor concluding that they do have the disease and this person does have a disease. A type 1 error. H0 is actually correct. The person doesn't have a disease, but the conclusion of the test is incorrect. So the doctor is telling a patient who's disease-free that they have the disease. That's the type 1 error. A type 2 error, in that case, H1 is correct. This person has the disease. The error is accepting H0 and telling the patient that they're disease-free when they're indeed not. Type 1 and type 2 errors. Rejecting H0 incorrectly for a type 1 and accepting H0 incorrectly for a type 2. Let's have a look at some more visual examples. In this example, the null hypothesis is that the patient is not pregnant. The alternate hypothesis is that the patient is pregnant. So, let's have a look first at the correct conclusions. So we can correctly diagnose someone as being pregnant. So H1 is correct, they're pregnant, and our conclusion is that they're pregnant. Or we can correctly diagnose someone as not being pregnant. So the patient is not pregnant, and we tell them they're not pregnant. What would the two errors look like? Let's start with a type 2 error. So H1 is correct, but we conclude that H0 is correct. So we have a pregnant patient, but we're concluding that they're not pregnant. What about a type 1 error? So H0 is correct, but we're concluding H1. The patient is not pregnant, but we conclude that they are. So hopefully this is an example that's easy enough to stay with you. False positive, false negative. Type 1 error, type 2 error. Okay, let's go through an example. So, reading through the scenario, and with these questions, part A should be a very familiar Year 12 question, or something based on the distribution you're familiar with. We're told that accidents occur on a stretch of motorway at an average rate of 6 per month. Many of the accidents that occurred involved vehicles skidding into the back of other vehicles. By way of a trial, a new type of road surface that is said to reduce the risk of vehicles skidding is laid on this stretch of road. And during the first month of operation, 4 accidents occurred. We're asked to test to see if this gives evidence that there's been an improvement at the 5% level of significance. So this is a standard Poisson hypothesis test. So we'll set out our parameter. X is the number of accidents in any month. Lambda equals 6 is the null hypothesis. Lambda is less than 6. There have been fewer accidents. That's the alternate hypothesis. Now, we're going to base our calculations on H0 being correct. Since we saw 4 accidents, we're looking for the probability X is less than or equal to 4 using lambda equals 6. That gets us 0.2851. We make our comparison. This is quite a large probability, way bigger than the significance level. We have insufficient evidence to reject H0. So we have insufficient evidence that the number of accidents has decreased. We're then asked to calculate a type 1 error for this test. Calculating a type 1 error is exactly the same as finding the actual significance level of the test. To find the actual significance level, we need the critical region. So we're going to use our calculators or the tables to find the critical region. To find the value where less than or equal to that value gives us a probability smaller than 5%, smaller than our significance level. So a bit of trial and improvement, and we get our critical region. X is less than or equal to 1. Now the probability of that critical region, 0.0174. Probability of a type 1 error, 0.0174. So you've been finding type 1 errors for a long time. The actual significance level. In part C, we're told if the true average rate of accidents occurring on the new type of road surface was 3.5, calculate the probability of a type 2 error. So a type 2 error would be us accepting H0. So rather than the critical region, rather than the rejection region, we're going to go for 1 minus the critical region. We're going to go for the acceptance region. So we're going to find the probability of greater than or equal to 2. But now we have new information. We now know that lambda should have been 3.5. So we're looking for the probability that x is greater than or equal to 2 using lambda equals 3.5. Okay, so from there we get 0.8641. So that's what we need to be able to do. Do a standard hypothesis test and then talk about the type 1 and type 2 errors. Calculate the type 1 and type 2 errors. Calculate the probability of rejecting H0 when you shouldn't have. Calculate the probability of accepting H0 when you shouldn't have. So I'll just put a few more examples up on the screen and you can have a think through them, how the type 1 and type 2 errors may occur, what they mean in the context. And I'll also put up some further consideration of the cost of a type 1 error or a type 2 error.